This video is part of the Rocketry Basics series. It is an example of how to select an engine for a given rocket design based on engine part number. You will need to be familiar with engine part number nomenclature before this example will make sense. Assuming you already know how engine part numbers work, let's see if we can use that understanding to select candidate engines for a hypothetical rocket design. We'll base our hypothetical design on NAR rule number 20, which is an altitude rocket. In other words, we are designing a rocket to achieve a maximum altitude. Let's assume that the engine mount was designed for 13mm engines. We'll assume that we've done a preliminary design and we've concluded that the mass of our rocket is going to be approximately 20 grams without the engine. And we have designed it so that it has reasonable aerodynamic efficiency. Since we are using a 13mm engine mount, we will obviously need to use a 13mm engine. There are probably some others too, but the 1/4 A3-3T, the 1/2 A3-4T, the A3-4T, the A10-3T are four candidate engines that could definitely be used given a 13mm engine mount. The one thing I would point out about these part numbers is there's one thing unusual about them, and that's that T suffix on the end. You only see that on 13mm engines. There's no good reason why, but all 13mm engines, or I should say most 13mm engines, have that T suffix on them. No other size engines use any suffix like that. So how do we know which one of these engines we want to use? The first consideration is the power level of the engine. Notice we have three different power classifications on these engines. This is a 1/4 A engine, that's a 1/2 A engine, that's an A engine, this is also an A engine. Remember, that letter tells you the power level. In this case, the A engines, both of these, have the same power rating, the same impulse rating. This engine is a 1/2 A engine, so it only has half the power, half the impulse that the A engines have, and the 1/4 A engine only has half as much as the 1/2 A does, or 1/4 of what the A engine has. So clearly, if you want a high-powered engine, you would pick either the A3 or the A10. Now, if you're going to compete in a 1/2 A competition, you obviously can't pick the A3 or the A10 because they're not legal. You may have to pick a 1/2 A if you're competing in a 1/2 A competition. Or you may even have to pick the 1/4 A if you're competing in the 1/4 A competition. But in our case, we're going to consider what's the engine that will give me the maximum altitude. We would go with the A engines because they have higher power levels. One of the common misconceptions is that this A10 engine is a higher power level than that A3 engine. A lot of people look at this and say 10, well that's more than 3, so therefore this must be a higher power engine. It's not. These two engines are both A engines, and if you go look up the actual impulse rating of these engines, you're going to find that these two are exactly the same. They're both 2.5 Newton-second engines. These two engines deliver exactly the same impulse, the same power level to the rocket. So theoretically, these two should drive your rocket to exactly the same altitude. There are some little details that are going to make for some subtle differences, but in general, these two engines have the same power level. So the A10 is not necessarily a better choice than the A3. It's more complicated than that. The next consideration is thrust, because it's the engine's thrust that determines how much mass the engine can safely lift. Understanding the details of just how much mass any specific engine can lift is, to be honest, beyond the level of this video. In a more advanced discussion, we will get into those details. But for now, we can just generalize it and say that the higher an engine's thrust rating, the more mass it can lift. In the case of our candidate engines, we can use these maximums as a guide. These numbers are derived from manufacturer data. Note that these are maximum gross launch masses. That includes not only the mass of the rocket itself, but also the mass of the engine. In other words, the total launch mass is what counts. Now, if we take a look at these engines one at a time, let's talk first about the 1/4 A engine. Ask the question, can we fly our 20-gram rocket on a 1/4 A engine with this much lift capability? The answer is no. It's because these 13 millimeter engines weigh somewhere between 6 to 8 grams. So we add that to our 20-gram rocket and we have to be able to lift somewhere between 26 and 28 grams. This engine can only lift 25. If I want to enter a 1/4 A competition with this rocket, I'm going to have to redesign it and reduce its mass. Now, 1/2 A engine, that'll lift 50 grams. The A3 will also lift 50 grams. Clearly, either of those engines would lift this rocket safely. The A10 can lift as much as 80 grams because it has a higher thrust. It has a thrust of 10 newtons, whereas these two only have a thrust of 3 newtons. The A10 clearly can lift this rocket, no problem. Now, the question we were trying to answer is, which is a better choice, the A3 or the A10? Both of these engines will lift that rocket, not a problem. So which is a better choice, the A3 or the A10? We still don't know. We're going to have to consider something else. The final consideration is ejection delay time. If we are designing this rocket to go to a maximum altitude, we really don't care where the recovery system is ejected, as long as the rocket is allowed to get to apogee before it's ejected. In other words, it could eject at its highest point, or it could eject sometime after that, and it's still going to go to its maximum altitude. However, if it were to eject before apogee, the parachute opens, it's going to prevent the rocket from going to its maximum height. So we do not want an ejection delay that's too short. If we look at the ejection delays for these 4 engines, they're all encoded in this last number. Notice the A10 only has a 3-second delay, whereas the A4 has a 4-second delay. If I design the best rocket I can to go as high as I possibly can, the A10 is likely to eject before it reaches apogee, which will make it not go as high as it should. The 4-second delay is preferred over the 3-second delay because that will give me more time to go to a higher altitude. So, the best choice between the A3 and the A10 is probably the A3. In general, for an altitude rocket, you want to go with a low thrust, 3 versus 10, and a long delay, 4 versus 3. In this case, this is probably the preferred engine. Now, to be honest with you, you probably should check out both engines. In other words, you should use a simulation program for your rocket, and you should simulate it with both engines to make sure that that's true. In the case of an altitude rocket, I'm pretty confident that the A3 is going to be the preferred engine. Okay, let's see if we can summarize all that and give you some general guidelines you can use in the future. In general, when you go to select an engine for your rocket, you will select the highest power class that will fit the engine mount. In other words, A, B, C, D. You'll pick the highest class that will fit the engine mount, or you'll select it based on the highest impulse allowed in the competition you're entering. Okay, to maximize altitude, you're designing an altitude rocket. Designed for lightweight. Obviously, the lighter it is, the higher it'll go. And select an engine that has a low thrust level but a long ejection delay. And like I showed in this example, that's a general rule of thumb. It's usually correct, but it always helps check everything out and simulate all possible engines that seem reasonable. Now, if you want to maximize duration, in other words, you're designing a parachute duration rocket, a rocket is designed to stay in the air as long as possible, it may be a little different. You're going to want to design for the biggest parachute, which is going to make your rocket heavy. So now you're probably going to be better off to select a high thrust engine with a shorter delay. A duration rocket is not going to go as high as an altitude rocket. The difference is it's going to come down much slower because it has a big parachute in it. So the high thrust, low delay engine is probably a better choice for those designs. Bottom line is, with today's simulation programs, you should always try to simulate several different engines in your final design so that you can select the best engine. And the truth is, when you get good at it, you'll find that by simulating multiple engines, you'll learn something about how to modify your design to improve it even more. This has been Rocketry Basics, an example of how to select an engine based on engine part number. After watching this video, you should download and/or print a copy of the General Rules for Engine Selection Summary for future reference.